So the idea is today to conclude the part on the coordinate reduction techniques, and basically this may as well be the last lecture of the course, meaning that next Thursday, next Friday, we won't have lecture. Okay, if we are able to finish it today. So let's recap a little bit what we saw last time. We introduced the so-called static condensation method, also called Gaian iron method. Gaian iron condensation. So the idea at the basis of this technique was to reduce the number of coordinates into a smaller set, first performing a division into master and slave coordinates. In particular, we underwent a Fourier transform. So this is a Fourier transform which we denoted with an overhead, so that we could reduce the number of the initial vector of coordinates. In particular, the equation of dynamics we made the assumption of a perfectly constrained model, so no rigid motion. Again, just to simplify the, let's say, the formulation, but I mean, retaining any kind of possible generality degree. The equation of dynamics read as such: we had Kmm applied over Qm plus Kms applied over Qs, but again, M and S denote the slaves and the master nodes, or coordinates eventually. Qs, and this was equal to F, the vector of the externally applied loads, which were insisting only on master nodes. So master nodes are the nodes to which we associate a master coordinate, of course. While for slave, we had the following. Equal to M Sm Qm plus MSS times Qs. And this was equal to 0, because here we have the hypothesis, if you remember, of no external load applied over slave nodes. Is another IP, if you remember. And we can call these two equations A and B. Okay, actually, let's put it like so. Okay. Now, the Gaian iron condensation was rooted on the fact that we divided Qs as a static part and a dynamic part. Static dynamic. And this was a dynamic contribution. Now, if from here, from equation B, we have that QS from equation B, sorry, considered for the static case. So for the static case, that's to say that QSD is equal to 0 and omega is equal to 0. We had eventually KSM QM plus KSS KSS, all right, equal to 0. And therefore, we could write that QSS was equal to minus KSS to the minus 1 applied to KSM over QM. And this we call as SS, okay? So basically a matrix which links the static part of the slave dynamics to directly to the master nodes. So this we already saw. In the same way, if we write equation B, rewrite equation B, making use of the new definition, we have the following. Ah, no, here you cannot see. Oh, it's nice. So, if we rewrite equation B introducing the matrix SS that we have just defined, we have the following. You can write QSD of course we are writing the second equation B for omega different from 0 in this case. QSD equal to omega squared times KSS minus omega squared MSS to the minus 1 applied over MSN minus M actually plus MSS over SS. Okay. All of this being multiplied to QM. Okay. Of course, this is omega different from 0. Now you see that the hypothesis of the Gaussian iron method is to consider that this QSD is equal to 0. Okay, so in condensation, we assume that QSD is identical equal to 0, meaning from the equation before that KSS minus omega MSS omega squared is very large. Okay? Because in the previous equation, it appears as an inverse multiplication. Okay? But what I just reported between round brackets is the eigenproblem of the slave nodes. This is the eigenproblem of the slave nodes. Meaning that when I say that it has to be very large, this term, it means that the dynamics of the slave node must happen at very high frequencies with respect to the bandwidth which I am interested into. Okay? So saying that KSS minus omega square is very large means that the dynamics of the slave nodes happens or is characterized at frequencies. I'm talking about the frequencies of the modes, at frequencies, so at eigenfrequencies, if you want. At eigenfrequencies, which are much higher than my frequency bandwidth of interest. Oops. Of interest. Okay? So if this is true, I can apply the Gaussian iron method. Okay? If this holds true, I can safely apply Gaussian iron method. Okay, but what is the consequence of this? Okay, because this we already saw last time. Well, we have that eventually Q, a vector of nodal coordinates, which we saw could be decomposed in QM and QS, can be eventually written as what? As the matrix of identity I and S multiplied all of it times the master coordinates, right? And this is actually the reduction matrix that I was looking for, which we can name as R Gaussian iron as subscript. These are the identity, times QM. Okay. Now you can see that this was a n times 1 vector. Okay. In this case, if the master node is L, for example, L times 1, we have our reduction is that L is typically smaller than N. So in fact, if you want, since we have introduced as the number of reduced number of degrees of freedom as M, so we have the number UFs is M. You remember we introduced it as M. And in this case, M is equal to L, which is smaller than N. Okay, so in this case, the reduced number of coordinates of the model exactly is equal to the master nodes, okay, to the number of coordinates which is associated to the master nodes. This is not always the case, so M does not always have to be equal to L, okay? We will see it now with the new method, the Craig-Benton method, okay? In any case, as a follow-up, we have that the new matrix, Gaussian iron, is what? If you remember, is the reduction matrix of Gaussian iron transposed, applied over the original matrix of stiffness times R, Gaussian iron. Okay, and in fact, if you want, this is, you can see this is already, this is an N times L matrix, no? So in fact, here you have an L times L. This is an L times M. N, sorry, this is an N times N, and this is an N times L. Okay, so we are reducing. Eventually, all of this, in order to solve the dynamics, we have to calculate the inverse of these matrices. This is really the highest computational part in solving the dynamic of this equation, that you have an inversion of matrices, which is nonlinear. So it's something very, computationally intensive to do. If you are able to reduce the number or the dimension of these matrices, it's something that allows you to gain a lot of in terms of computational costs. And the same goes for the mass. It's an L times L as well. So Gaussian iron. Remember that these two equalities that I'm writing now comes from the hypothesis of considering conservation of the kinetic and of the elastic energy. Okay, if you remember, we saw it last time. From the conservation of the kinetic energy, of the elastic energy between the reduced and the original system, you derive a relationship between the reduced and the original stiffness and mass matrices. Okay. Okay. So this is the Gaussian iron method. Very simply put. Now, the idea, what is it? The idea is that sometimes this kind of reduction can be too harsh. That you cannot avoid losing so much information. For example, because the dynamics of the slave nodes somehow falls, at least in part, within your frequency bandwidth of interest. Okay? So now the question is, how can I, at least partially, selectively introduce, part of the dynamics of the slave nodes within my model, but only the part of the dynamics of the slave nodes which is of interest to me. That's to say, the modes, the eigenfrequencies, which fall within my bandwidth of interest. How can I do that? This is achieved through the Craig-Benton condensation method, or also called the dynamic condensation, okay, which we will see now. aka the Craig-Bampton method. Okay. Now, it's actually quite straightforward if you think about it. So, when you reduce the number using coordinates using the static condensation, as we have said, you do the following. Okay, you do this: master slaves, and this is again, as said, R Gaian iron times Qm. Now, if you write it coordinate by coordinates, you can write as R, this is a vector, 1, for example, Gaian iron, times Qm1, plus what? R2, and then I'm going to explain what this is, Qm2, until I arrive to R L Gaian iron QML. Okay, what is it that I'm doing here? Well, basically I'm just rewriting, if you see this. So this is a column. This is the first column of the matrix RJI. Okay, so basically I'm rewriting this product here as, you know, term by term. Okay, if you look at that, isn't it somehow similar to the restricted formulation that we did, which we had the psi vector times the q in our restricted formulation? It's actually formally identical, no? So, in fact, if you think about it, it is like if the qm, so the master coordinates, are what we thought of as q, so the reduced elastic coordinates, okay, which in theory should be infinite, but now they are reduced. And our r vector here, the small letter r, is basically our vector of shape function, if you want, okay, in this analogy. So you can think of R here, the column vector R, R1, R2, R3, as the shape functions which are associated to the master coordinate x or epsilon, whatever, when that coordinate has a value of 1. Do you remember when we introduced the shape function, the true advantage of introducing the finite element method in our formulation was that first the coordinates acquired a physical meaning, which was apparent, and then also the vectors were basically built as everywhere else they were 0, but 1 in correspondence of the node of the coordinate. Okay, so in this case you can think of this r vector, this one or this one, as the displacement field associated to the correspondent master node, where everywhere else they are 0, but they are 1 in correspondence of that node. Okay, we can use to better explicit this concept an image. Okay, so we can think of this are the displacement field associated to Qm k. Okay. In particular, we can do the following. If you think of you see, our wing, in the analogy of a wing, we are condensating the wing to the nodes of the root of the wing. Okay, you're basically our RK is basically the mode, the displacement field over the wing, where you have 0 everywhere on all the slave nodes, but it is 1 on the correspondent master node. Okay, as you can see here. So for example, here you can do the following in this analysis. So for example, this is, let's say here you have 1, 2, 3, 4, 5, 6 master nodes. You see, you have 1, 2, 3, 4, 5, and 6 master nodes. Okay, and this is RK, IJI, if you want, of the fifth coordinate. You see, because it's 1 in correspondence of the fifth master node, and it's 0 everywhere else. Did you remember when we introduced the finite element method? We said that our vector in this series expansion should be 0 everywhere, but in the node of the correspondent coordinate, where they were equal to 1. And this is again the same. So here, for example, we have 1, 2, 3, 4, 5, and 6. These are the master nodes again. And this is again R GI 4. Okay. So all of this to say what? That basically, when you are using the static condensation method, you assume that you can represent the dynamics of all of the structure, in this case the wing, only as a linear combination of these mode shapes here, okay, in which you have 0 everywhere, but in the nodes, in the master nodes. And sometimes it's not, as we were saying, sometimes it's not sufficient, okay? Okay. Sometimes we need to include some, and this is very important to say some, because then we will, let's say, explicit it more carefully. Some of the dynamics of the slave nodes into our reduced model. How can we do that? Well, it's actually quite easy, because we consider, again, the dynamics of the slave part. Okay. Okay, so we consider again the eigenproblem. KSS applied over minus omega squared times MSS. Okay, equal, let's say, if this is, for example, let's say, K, this is Z, the Z vector, K, equal to 0. For K going from 1 to 2, for example, to number P. okay, where this is the kth eigenvector of the slave nodes. Okay? So, and this is the number of slave nodes. So that P plus L is equal to what? If P is the number of slave nodes and L was the number of master nodes, the master node plus the slave nodes is the number of what? Of N, not the total number of the nodes. So this is the number of master. And this is the number of nodes, the total number of nodes. Okay, so the idea is to use as additional shape functions some of the eigenmodes of the slave problem, of the eigenmodes of the slave problem, meaning, for example, if we introduce this, where is it? Here it is. So if you look at this, here you have the first 6 eigenmodes of the slave part. You see? Now you can say that you can introduce some of these displacement field as vector in your expansion. So to introduce some of the dynamics of the slave part of your model. Which one? How many? It depends on the associated eigenfrequency. Okay, so for example, if I'm interested in the response of the structure from 0 to 100 hertz, if there are some of the eigenmodes which have a frequency which falls within 0 and 100 hertz, I will introduce it. For example, the first 3 here, I don't know, 4. Okay, and this will enrich my model, my static condensation, introducing the part of the dynamics of the slave node which I care about. So only the one which falls within my frequency bandwidth of interest. Okay? So, again, what I do is writing the following. I consider sum of the eigenvector ZSK, so of the slave part, in my expansion. So what do I mean? I mean that when I write Qm equal to Q Gaian iron plus, so this is what the part that we had before, no? Plus, for example, what? ZS1, another coordinate which we call eta, and then we will see why we call it eta. Eta S1 plus, for example, Z S whatever, for example, we can call it R times eta S R. Okay, So, for example, I consider the first R modes, okay, in my expansion. If I have to write it in a compact way, I can write the following. Eta, or eta, they are basically the modal coordinates. No? They are coordinates which are not anymore associated to the displacement of a single node, but because they are associated to what we are seeing here. You see here. So the overall, this is an overall displacement. So when you talk about modal coordinates, they are not anymore in the sense of the frame coordinates. Okay, you lose somehow the actual physical meaning. Okay, it's just a proportionality coefficient, if you want, proportionality coefficient which multiplies the mode shape. Okay, but again, it's a mode shape which characterizes the dynamics of the slate part for the contribution which I'm interested into retaining. Okay, so in a more compact way, you can write that Q slave static is again S, as we have seen before, times Qm. And this comes from Gaussian iron method. Okay? The dynamic, this way, is not anymore 0. Actually, let's write it like so, which is less confusing. Is Z S times eta slave. Well, this is just a matrix whose columns are the eigenvectors we are interested into. This is a matrix whose columns are the eigenvector Z, S, K. And this is the vector of nodal coordinates, not nodal anymore, modal coordinates. And you see this is different from 0, typically. Okay, so it's not anymore as the Gaussian iron approximation. If you do this, your new matrix of reduction is different, no? In this case, we have that my Q, which is again divided in Q master and Q slaves, can be written as such. The master, of course, is always equal to the master. But then we have two components, because here we have 0, here we have S, and here we have Z, S. As a multiplication to what? To the master and the eta, the modal coordinates. Okay. This is my new vector, which I call Craig-Bampton, in this case. And this is my new QR. You see now, my vector of reduced coordinates doesn't coincide anymore to the master nodes, as in the static condensation, because in this case you have the master plus the modal coordinates. So in this case, M is equal to L, the master, plus R, the number of the modal coordinates. And this, the number of okay, and again, we have finally that our matrix reduced of Craig-Benton is again the transformation matrix of Craig-Benton applied over the original K transposed over RCD. And the same goes for the mass. Okay. Now the question is, how do we choose the number again of modes? Again, it depends on the frequency bandwidth of interest. Okay. It depends on the frequency bandwidth of interest for the dynamics of my problem. Okay. So everything that falls within my bandwidth of interest, I should include. Okay. So basically, this closes our lecture and the course. So we stop here the recording.